Okay, this is 10.3 for Honors Math 3, the angle addition laws, or the sum and difference formulas. I am not deriving the formulas for you. We are just telling you what they are. These are something that you do need to have memorized, and I am also going to be trying to help you with that. So the first one we're going to take a look at here is sine of angle addition, and this is sine of alpha plus beta. If you don't like using alpha plus beta, you could use a U and a V, but sine of alpha plus beta. And so here it is, sine cos, cosine, sine cos, cosine. So what do I mean by that? It's sine cos, cos, sine. And then we have to put the angles in because the trig function is meaningless without the angle. So it goes in order. So alpha, beta, and then we have something in between. And sine starts with an S, and so it is sine same, or same sign. So if there's a plus here, there's a plus over here. Now, what makes that really nice is the fact that if it happens to be angle subtraction for sine, then we don't have some new formula. All we have to do is just remember that sine same, and so it will be minus there as well. But otherwise, it's exactly the same. So really, I think the easiest way to memorize this is just to kind of say it out loud each time you do one of these problems. So sine of angle addition, sine cos, cosine, and then the angles, alpha, beta, and sine same. Okay, so next we have cosine, of alpha plus beta. And again, it's just kind of how it sounds, and the way it goes, it's cos, sine, sine. Cos, sine, sine. And so cosine, sine, sine. And again, the angles go in order, alpha, beta. And then cosine starts with a C, cosine, change. So if it's a minus over here, if it's a plus over here, then it's a minus over here. And again, what's really nice is if we remember the cosine change, then if it's a minus, so angle subtraction, so alpha minus beta, then it's going to be a plus over here. So let's see, let's write out what we said over here again. This was sine same, or same sign. And cosine change. Okay. And finally, we have the tangent of angle addition. So tangent of alpha plus beta. And unfortunately, it doesn't just kind of roll off the tongue like the others do. But there is one thing that's at least a little bit nice about it. But here it goes. Tangent up top. Notice I'm leaving a space there in between. And on the bottom, we have 1 and a space, and then tangent. And we're going to be multiplying the tangents down here on the bottom, so don't leave much of a space. The angles, again, go in order. So you got alpha and beta. So alpha, beta up top, and you also have alpha and beta on the bottom. Okay, now, like I say, it doesn't roll off the tongue like the others two do. But there is one thing at least that's kind of nice. Now, obviously, tangent, we know tangent can be written as sine over cosine. And so looking back on what we did before, sine over cosine, so same, the signs are the same over change. So same over change. Same over change. Now, again, that means if it's tangent of angle subtraction, then it's still same over change. So those are the three angle addition laws for trig functions. Okay, so let's do some examples of some of the things that you'll be using the angle addition laws with. So evaluating some trig functions without scientific calculator. Now, previously, we have only been able to evaluate trig functions with 30-degree reference angles, 45-degree reference angles, 60-degree reference angles, and the quadrantal angles as well. Because of the angle addition laws, we now have some other angles that we're able to evaluate them without a scientific calculator. And so, but what we do want to maybe keep track of is those 30-degree reference angles, which are 30 degrees, 150 degrees, 210, and 330 degrees. The 45-degree reference angles, which are 45 degrees, 135, 225, and 315 degrees. And the 60-degree reference angles, so 60, 120, 240, 300. Because we're going to be using combinations of those to come up with a sum or a difference that gives us the angle that we're trying to evaluate. So, for example, if we're trying to do sine of 165 degrees, can we pick out two angles that we could do a sum or a difference? And it works either way. So, for example, the first one that I'm noticing that 30 degrees and 135 degrees has a sum of 165 degrees. But we could just as easily do 45 degrees and 120 degrees. Or if we found any other pair that if we did the sum or the difference and it was 165 degrees, it would work. Now, it is kind of nice to use as many quadrant 1 angles as you can, just to make life easier on yourself, but that's just a suggestion. So, for example, I noticed the 30 degrees and 135 degrees first. So let's go ahead and do that. So I'm rewriting the problem as sine of 30 degrees plus 135 degrees. Okay, so now I have it written as sine of angle addition, and so sine cos, cosine. And alpha beta, so 30 degrees, 135 degrees, 30 degrees, 135 degrees, and then sine same, and so there's a plus there in the middle between them. Okay, now at this point, I like to do some parentheses because we're evaluating each one of these. Now we want to keep in mind, and if you need to have in front of you a sketch of your reference triangles, but we're going to be evaluating all of them. So first off, let's figure out the signs, plus or minus. 30 degrees, we know that's quadrant 1, so we know it's going to be positive. 135 degrees, quadrant 2, what do we know about cosine in quadrant 2? It's negative. 30 degrees, quadrant 1, it's positive, and 135 degrees is quadrant 2, and sine we know is positive in quadrant 2. Okay, so sine of 30-degree reference. So envision that 30-degree reference angle, sine 1/2. While I'm on it, let's go look at the other 30-degree reference angle. Cosine of 30 degrees, √3/2. Now let's go to 135 degrees, which is a 45-degree reference angle. We've already got the sine on it, so it's negative here. So cosine of a 45-degree reference angle is 1/√2. Obviously, you could rationalize the denominator as well. Sine of a 45-degree reference angle is 1/√2. Okay, so we have negative 1/2√2 plus √3/2√2, which is -1 plus √3/2√2, which is actually okay. Not a problem with that. Rationalizing the denominators is not a hugely important thing as we get to higher levels of math. On the other hand, sometimes when it's a multiple choice test, you still have to be able to rationalize at a moment's notice. So be prepared to be able to do that. We'd multiply top and bottom by √2, and that would get us negative √2 plus √6 all over 4. So when called upon, make sure that you're able to do that. Okay, next problem that we're going to do, instead of degrees, we need to be able to do it in terms of radians as well. If you need to be able to write out sort of like what we did with degrees, the 30-degree reference angles, so you got pi/6, 5pi/6, 7pi/6, 11pi/6, and so on, and you can go ahead and do that as well. But let's say we have cosine of pi/12, and so pi/12, that's a pretty small angle. We're probably not going to get a couple angles that we can do a sum of. But if we think about it, if we do subtraction, and so for example, pi/4 and pi/6, so if we did pi/4 minus pi/6, pi/4 minus pi/6, so 3pi/12 minus 2pi/12 would be 1pi/12. Now, that's one way we could do it. I did 45 and 30-degree reference before, so how about if I do pi/3 minus pi/4? So that works as well. So cosine of pi/3 minus pi/4. Because if you think about it, 4pi/12 minus 3pi/12 is 1pi/12. Okay, and this is cosine of angle subtraction. So cos, cos, sine, sine. Alpha, beta, so pi/3, pi/4, pi/3, pi/4, and cosine change. So since it's minus here, it's going to be a plus there. Now, pi/3 and pi/4 are both quadrant 1 angles, and so therefore we know that all these trig functions evaluated at those quadrant 1 angles, those are all going to be positive values. So cosine of pi over 3, envision that pi over 3 reference triangle, and it's 1/2. I'm going to go ahead and do the other pi over 3. That one's going to be sine of pi over 3, which is √3 over 2. And now to the pi over 4 reference angle. So cosine of pi over 4 is 1 over √2, and sine pi over 4 is 1 over √2. And we already have a common denominator built in. So we have 1 plus √3 over 2 √2. Again, which is not a problem, but we should be ready to rationalize it and recognize it if we need to at a moment's notice. Multiply by √2 top and bottom, and you would get √2 plus √6 all over 4. Okay, let's do one more. Let's do tangent. We haven't done tangent yet. So part C, tangent of 255 degrees. Okay, so 255 degrees, so probably we're looking back up here again, and 255, so I see 225 and 30 degrees, and that would be 255 degrees. Always make sure that it has a sum or difference of what you're supposed to. It's really sad when we see some students that they don't even pick out two angles that have the correct sum or difference. So be careful with that. So it's tangent of 30 degrees plus 225 degrees. And so tangent of angle addition. Okay, so tangent, 1, tangent. Okay, and again, alpha, beta, so 30 degrees, 225 degrees, 30 degrees, 225 degrees, and then same over change. So there's a plus here, so same over change. Okay, so we've got parentheses here. I'm going to be filling in each one of those angles. And the quadrant 1 angles, we know they're always positive, so tangent 30, we know it's positive. And tangent 225 degrees. Well, 225 degrees is quadrant 3. What do we know about tangent quadrant 3? It's positive in quadrant 3. Okay, tangent 30 degrees, 1 over √3. And let's stay on the 30 degrees. So tangent 30 degrees, 1 over √3. So this is one of the things that's actually a little bit nice about tangent, because really there's 4 blanks there, and the 4 blanks, you only have 2 different trig functions to evaluate, unlike the sine of angle addition and cosine of angle addition. So both positive, 1 over √3. And then tangent of 225 degrees, so tangent of a 45-degree reference, which is 1. So we get 1 over √3 plus 1 over 1 minus 1 over √3. Okay, radicals in a denominator are not a problem, but we can never leave a complex fraction and expect to get full credit. So we've shown you how to clean these things up last year and this year. So if we multiply top and bottom by √3 over √3, you can do over 1 and over 1 if that's helpful. You don't have to do the over 1s. We distribute, and we end up with 1 plus √3 over √3 minus 1. Okay, so radicals in the denominator, not a problem. And so yes, we could potentially leave the answer like that. However, again, if we're trying to match things up to multiple choice, and sometimes they might rationalize the denominator. So let's remind ourselves how to rationalize something like that. So when you you have something like root 3 minus 1 in the denominator, you can't just simply multiply top and bottom by root 3. You're still going to have a radical in the denominator. So think of the conjugate of the denominator when you have root 3 minus 1. So the conjugate is root 3 plus 1, and then you have to multiply the top by the exact same thing because we're multiplying by 1. Okay, so if we do that, and I'm out of space, so I'm going to write that over here. So we would get, now the conjugate pair, root 3 minus 1 times root 3 plus 1, root 3 times root 3, you get 3. The middle terms eliminate anytime you're multiplying a conjugate pair, and then minus 1. So the denominator is going to be 2. Up top, we get 1 plus root 3 times root 3 plus 1. So we get root 3 plus 1 plus 3 plus root 3. So we have 4 plus 2 root 3. Now, 2 goes into both of those evenly. We always look to reduce a fraction, and this would be 2 plus 1 root 3, or just 2 plus root 3. Final answer. No radicals left in the denominator. And so actually, if you ever have multiple choice with something like that, I mean, this is what the final answer really should be. Now, sometimes when we're working with the angle addition laws, sometimes we have to expand the problem, sort of like what we were doing on 1, A, B, and C, where we had to expand to be able to use it to our advantage. Other times, we need to be able to recognize the pattern and to be able to condense the formula. And so it just kind of depends on the situation. So directions are simplify, simplify as much as we can. Now over here, and sometimes it's kind of just good to take a look at the big picture first. I mean, if we started looking at the individual components, you're probably looking, you're going cosine 65 degrees, cosine 10 degrees. We don't know how to work with 65 degrees or 10 degrees. But if we look at the big picture, and I've got cos, cos, sine, sine. And we go, oh, cos, cos, sine, sine. That's my cosine of angle addition, or is it subtraction? Well, it's one of those. So this is equal to cosine of, now let's figure out whether it's cosine of angle addition or angle subtraction. So cosine change. And so since it's plus here, that means it's going to be minus here, because cosine change. Now, it's important for us to keep the angles in order, and so alpha, beta, and so they're all matching in that correct order. And so 65 degrees minus 10 degrees. And now that we have those two angles inside the parentheses, I can actually do the operation with it, and I've got cosine of 55 degrees. And really, that's all we can do with this one. Now, on the other hand, I know that some of you, maybe all of you, were noticing that cos, cos, I mean, that's multiplication, and we know that multiplication is commutative. And so you might be saying, well, what if it had been cosine 10 degrees and then cosine 65 degrees? And then the same thing over here, if it had been sine 10 degrees and sine 65 degrees. So let's take a look at that situation. You know, what if it had been that order instead? And so if it had been that order instead, where we're doing the cosine 10 degrees, cosine 65 degrees, plus sine 10 degrees, sine 65 degrees, does that mean that it's changing the answer? Because it wouldn't be very good if it was changing the answer when we're doing a mathematical operation that would be okay. So it's still cosine of angle subtraction because cosine change, but alpha, beta, so 10 degrees, 65 degrees, and right now we would be having cosine of negative 55 degrees, but don't we have some opposite angle rules? And what's the opposite angle rule for cosine of a negative angle? Well, cosine of a negative angle is the same as cosine of the positive angle. And so that's good for us because we got the exact same answer either way. Let's take a look at another problem. Same directions. Directions are to simplify. And so this is problem number 3. So cosine 200 degrees, sine 50 degrees, minus sine of 200 degrees, cosine of 50 degrees. So again, if you're just kind of looking at the angles, you might be saying, yeah, there's nothing really we can do with them because those aren't angles we know how to work with. But if we look at the big picture, we go cosine, sine, cos. Wow, that's really close to something. Is it a pattern that we know right at the moment? Not right at the moment, but multiplication is commutative. We talked about that on the last problem. And so cos sine could be written as sine cos. And then the same thing over here, we could change the order of that as well. The minus is not changing, but we have cosine 50 degrees, sine of 200 degrees. So now it's sine cos, cosine. We go, oh yeah, we recognize that. So it's sine of angle addition or subtraction, one or the other. So sine of, nice big set of parentheses. Now, sine same. So there's a minus here. So it's sine of angle subtraction. And now when we are subtracting, we got to be careful and make sure we get the angles in order. Now the last problem we saw, it didn't really matter, but set it up correctly each time because it does matter when you're subtracting. Subtraction is not commutative. So alpha, beta, so it's 50 degrees minus 200 degrees. Okay, well, 50 degrees minus 200 degrees is negative 150 degrees. Now, what's the negative angle rule for sine? Well, it's almost like you're factoring out the negative one. That's not really what's happening, but it almost kind of looks like that. So negative sine of the positive angle. Now, at this point, are we done? Well, I don't know. Take a look. Is 150 degrees an angle we're supposed to know how to work with? We look and we go, oh, yeah, actually it is. It's a 30-degree reference angle, quadrant 2. So quadrant 2, 30 degrees reference. And so we still have the negative out front, so negative. But what is sine of 150 degrees? Well, quadrant 2 for sine we know is positive, and it's a 30-degree reference, and so sine of a 30-degree reference is 1/2. And so overall, the final answer is negative 1/2. And so if you get down to the end and it's an angle that we're supposed to be able to work with, 30-degree reference angle, a 45-degree reference angle, 60-degree reference angle, or maybe even a quadrantal angle, then finish it off, and you won't even have any trig in the final answer anyway. Let's try one more of those. Number 4. Okay, so number 4, we've got tangent 80 degrees times tangent 20 degrees minus 1 over tangent 80 degrees plus tangent 20 degrees. Okay, so kind of reminds us of the tangent formula, only it's flipped, right? Of course, we have taught you how to flip a fraction. If we want to flip a fraction, you just say 1 over, and then you flip the fraction. So this would be tangent 80 degrees plus 20 degrees, tangent 20 degrees, over tangent 80 degrees, tangent 20 degrees, minus 1. Now that's looking a lot closer to the tangent formula. So I've got tangent of alpha plus tangent of beta up top. But on the bottom, it's tan alpha, tan beta minus 1. And normally we have the 1 out in front. So, well, if we factor out a GCF of negative 1 out of the very bottom, so I'm factoring a GCF of negative 1 out of the very bottom here, and that would leave me with 1 minus tangent 80 degrees, tangent 20 degrees. Now, we've talked to you about the fact that we try not to leave negatives in the denominator, so this negative, we could take it all the way up to the numerator, and we've got negative 1 over tangent 80 degrees plus tangent 20 degrees over 1 minus tangent 80 degrees, tangent 20 degrees. Now, at this point, the stuff in the denominator matches the tangent of, is it angle addition or angle subtraction? Well, look at the signs. Same over change. Same over change. And so, this is tangent of angle addition. Same over change. So, it's angle addition. So, it's 80 degrees plus 20 degrees, which is 100 degrees. So negative 1 over tangent 100 degrees. Now, is 100 degrees an angle we know how to work with? No. But we never leave a fraction if we don't have to, and we certainly don't have to leave a fraction here. What's 1 over tangent? Cotangent. So negative 1 over tangent is negative cotangent of 100 degrees, and that is the final answer. Okay, so I've given you the basics so far of how to be able to deal with it, but let's take a look at some of the problems here. 1 and 2, it's telling you to just do exactly what it's telling you to do. Just show that sine of alpha plus beta. Using the formula, sine cosine, show that it does not equal sine of A plus sine of B, and plug in pi over 3 and pi over 6 for A and B. And so it's just kind of telling you exactly what to do. 3 through 5, you're doing sine of 195 degrees, cosine of 195 degrees, tangent of 195 degrees. And you'll need to use your angle addition or angle subtraction formulas to be coming up with each one of those angles. I did some samples like that too. 6 through 10, I just got finished doing some examples of that kind of stuff. Okay, 11 through 13. Solve for all x such that x is an element of 0 to 2 pi. Okay, we've been doing this kind of stuff. It's just solving for all x between 0 and 2 pi. And then part B, you expand it so that we find all x with no boundaries, in other words. So we've been doing that sort of thing. And then 14 through 15, verify. So trig proof. Choose one side or the other, work with it step by step until you get the other side. Again, suggestion, start with the messier side, work to the cleaner side. And hint, you'll need to use angle addition laws. Let's actually do problem number 12, or at least most of problem number 12 together, maybe all of it. Let's go ahead and do that one together. Okay, so I've already got it written out. and cosine of angle addition minus cosine of angle subtraction equals 1. So there's no factoring we can do. Looks like we just need to do expansion using cosine of angle addition, cosine angle subtraction. So cos, cos, sine, sine. Cos, cos, sine, sine. And alpha, beta, so x pi over 4, x pi over 4, and cosine change. So plus here, minus there. Now, I'm going to go ahead and use parentheses so we can keep track of everything. So that's the cosine of x plus 4. Minus parentheses, and again, cos, cos, sine, sine. Alpha, beta, so x pi over 4, x pi over 4, and cosine change. So there's minus here, which means there's a plus right there. Okay, so equals 1. Now, if we distribute the negative, what do we notice happens? The cosine x, cosine pi over 4, I've got a positive 1 here on the left, and I will have a negative 1 there on the right. And so those eliminate each other. Now, if I distribute the negative, the sine x and sine pi over 4, they do not eliminate each other, but I have negative 1 sine x sine pi over 4, and I have another negative 1 sine x sine pi over 4. So we actually have negative 2 sine x sine pi over 4, and don't forget about the equals 1 over there. Okay, now sine pi over 4, that's something we're supposed to be able to work with, and so somewhere along the way we need to go ahead and deal with that. I could move the negative 2 right now, I could wait, it just depends on the person. I think I'll go ahead and move the negative 2 right now. We'll divide by negative 2, so I get negative 1/2, and I also have sine x, and sine pi over 4, it's quadrant 1, so positive 1 over root 2. Now we're trying to solve for x, so we probably want to try to get the sine x by itself. So if I move the positive 1 over root 2 to the other side, we have sine x equals negative 1/2 times positive root 2 over 1. Okay, now we can leave it like that, negative root 2 over 2, but we might also want, I mean, sometimes, you kind of like it's rationalized. So if you can recognize it, negative 1 over root 2, so sine of x equals negative root 2 over 2, or negative 1 over root 2. So we know that sine is positive, quadrants 1 and 2, negative quadrants 3 and 4, so it's quadrants 3 and 4. And 1 over root 2, that's a pi over 4 reference. And so part A, x, quadrant 3, pi over 4 reference, 5 pi over 4. Quadrant 4, pi over 4 reference, 7 pi over 4. So there's the answer to part A. Just a bit of a sketch just to keep track. You can see that the two angles are not directly across from each other. So as far as part B goes, it will take two separate equations to be able to write that out. So we've got x equals 5 pi over 4 plus 2k pi. And we've also got x equals 7 pi over 4 plus 2k pi, where k is an integer. So this is stuff that we have done before. It's just now we're incorporating the angle addition laws into it.